So in this case, well, let's find out the integral that will compute the volume using the order dz, dy, dx. And we have this region, x varying between 0 and 2, y varying between x squared and 4, and z varying between 0 and 2 minus x. All right, so the good thing about this integral, so volume equals, is that this is already giving us the triple integral in this order, because check this out. This z, so the first iteration of the integration with respect to z, well, the limits have to be function of x and y, or simply x or simply y. Is that the case for these bounds right here? Yeah, so it's z varying, I mean, it has x only, right? And what about the middle integral? It's that second integral with respect to y can only be a function of x. And what do we have? We have y bounded above by 4 and bounded below by x squared. So it's actually the limits, right? And x, the remaining variable, it's constant. So we got this. 0 to 2, x squared to 4, and 0 to 2 minus x. That's it. Right? That's it. Okay. So no, we're not going to compute the integral. They're just asking us to set up the integral. All right. So let's see. Part B. Write the triple integral using dv equals dz, dx, dy. So we will reverse the order, interchange the x and the y. And here is where we need to have a look at what's going on in the xy plane. So number one, let's look at this x squared less than or equal y less than or equal to 4. Let's find out what is that really telling us. Okay, so what was that? Y. So if we break this up into two inequalities, this is telling us y greater than or equal to x squared and y less than or equal to 4. Okay? So what do we have in this case? Well, this is going to be a parabola opening up. Alright, that's our y equals x squared. Alright? And well, y equals to 4 and below. That's our horizontal line right here. Alright, are you guys following me up to this point? So that's what's going on in the xy plane by just looking at this bounds for the y variable. Alright, well, so in this case we need to reverse the order of this equation, or rather of the order of integration. So in this case, notice also x is varying, okay, comma, x varies between 0 and 2. That is, we're going to go only with the right side of the parabola, not both sides of the parabola, right? Only that side. And in this case, well, if we look at y equals x squared, well, this is x equals plus or minus the square root of x. So by the square root property, we should technically get two solutions, the negative and the positive. But because in this case, because of the limit in the direction of x, 0 to 2, we only care about the positive. Only y equals the square root of y. X equals the square root of y, not y equals root of x, all right? So what are we going to have in this case? Well, so redefining the integral, the limits rather. Okay, z will still vary the same way. So z varies between 0 and 2 minus x. And what's next? In this case, y will vary between, in this case, it's going to be, what do I have for my limits? Okay, so that's going to be 0 and 4. Because if we, this is y equals to 0, and this is y equals to 4. Right, those were our horizontal line. So in the vertical direction, that's what we have. And in the x direction, we have x varying between 0 and root of y. But be careful with the order once we start writing the triple integral. Okay, so that's a volume in this case we want, okay, triple, that's dz, dx, dy. So z which varies, z which is a function of x and y, well in this case it only contains x, 2 minus x, and 0 below. And what else? So the limit with respect x, careful, the limit with respect x, because that's the next variable. So that's from 0 to square root of y. And y varies between 0 and 4. Right? So all we did is simply change the function y, which depends on x, to a function of y, and reverse that idea, reverse those limits. The limits with respect to z, they remain the same. Okay? And well, those were some examples on triple integrals. Let's look at one of the applications, finding the average value of a function. We did that in Calc 1, 1 over b minus a, which is the length of the interval, times the integral. We did that last week or a couple of weeks ago with two integrals, which in this case is 1 over the area of the region times the integral. All right? And well, in a triple integral would be very similar, but in this case is 1 over the volume of the box where we're integrating. All right? So let's look at one brief example. Find the average value f of x equals z cubed plus 4 over the rectangular prism in the first octant bounded by the coordinate planes, and the planes x equals to 2, y equals to 3, and z equals to 4. So essentially, we are integrating over the following solids. So that's 1, 2, 1, 2, 3, and 1, 2, 3, 4. All right, so that's going to be over this rectangular box. All right, that came out okay. So that's the rectangular box over we are going to find the average value of the function. So, well, for the average value of the function, which can be denoted f with a bar, that's 1 over the volume of the region D times the triple integral of f of x, y, z with respect. Well, let's call it, how did we call it? dv for now, right? dv. And well, let's find the volume of this box. So the volume, so that's 2 times 3 times 4. That's 24. All right? So that's going to be 1 over 24, the triple integral of the function z cubed plus 4 We can do dz dx dy, dy dx dz, whatever order you want. But I mean, we're already used to dz, dy, and dx. And in fact, any order is not going to make the integral more complicated or easier, because look at the limits of the region. They're all constants. So it's vertically simple, it's vertically horizontal, everything, right? From whatever perspective you look at this region. So we can just go about 0 to 2, 0 to 3, and 0 to 4. And let's integrate. This one we're going to compute the integral. So that's 1 over 24 times the integral from 0 to 2 and from 0 to 3. And well, the integral with respect to z, that's going to be z over c to the 4th over 4 plus, not minus, plus 4z evaluated from 0 to 4 dy dx. Right? And what else? So upper limit minus lower limit, the integral from 0 to 2 and from 0 to 3, and that's going to be 4 squared, which is going to be a big number. Okay, so 4 squared, 4 to the 4th over 4 plus 4 times 4 minus 0. How about minus 0? Because it's the lower limit is 0 and everything will get zeroed out in this case. And that's still dy dx. Okay, so that's going to be, so 4 to the 4th divided by 4, that's 4 cubed, which is 64. And 64 plus 16, isn't that 80, I think? Okay, so 80 minus 0, that's just 80. So that's 1 over 24. And from 0 to 2 and 0 to 3. And that's 80 dy dx. All right, and then from here, what about integrating this with respect to y? So that's just 1 over 24. Integral from 0 to 2. And that's 80y evaluated from 0 to 3 with respect x. All right, so as usual, upper limit minus lower limit. Zero to 2, so that's 80 times 3 minus 0. And that's 240. 1 over 240, 1 over 24, 0 to 2, 240. And instead of integrating 240 dx to get 240 dx, how about we divide out 240 with 24 and have a 10 outside of the integral? I think it's much better to do that. And that's a 10 integral from 0 to 2 dx, and that's 10 x from 0 to 2, 10 times 2 minus 0, and that's 20. So that's the average value, 20. All right. And I think this concludes the section, right? Is that right? Okay, there's something more at the bottom of the page about applications, but that's something I mentioned last time, when we were working on the meaning of the triple integral. When the triple integral has a 1 in the integral, in a similar way that we define the area, that triple integral will define volume. But if that triple integral has a function f of x, y, z, that function of 3 variables, it's actually the density function. And again, you can think, for example, a rock or something that doesn't that is not made of a uniform material. You know, different points on that rock or that solid will be more dense than others. So in this case, we have a material with a variable density. Well, that variable density is given by this function, depending on the point in the space. Okay. But we're going to look at this when we get to 16.6. In the meantime, let's go to 16.5. I don't know if I want to touch base on, well, let's do at least a little bit of cylindrical coordinates. Well, so, okay, so double integrals, at the beginning, some of them, well, were tedious to compute rather. And as an alternative, we got this transformation into polar coordinates to, in some cases, simplify the problem, or in some cases to even be able to perform the integration, because in some setups of the integral may yield to integrals that we cannot evaluate with the methods that we have, because we're missing one power of x, so we can perform the UDU substitution. That's one issue we got in one of the integrals when we got to polar coordinates. However,